Good evening. I had a request to read through an organic chemistry textbook, and so I brought one of these home from the office, and I selected a particular section from a chapter that we're going to read through and talk about. But before we get started, I wanted to show you something that is absolutely adorable. He's right over there. There he is. You know, I really should zoom in on him. Look at that guy. Okay. He is just going to sleep quietly while we read through some chemistry. All right. Let us take a gander at this section. This is an older edition, but this is a textbook that's used in many universities for organic chemistry. So the chapter is one of the earlier ones, and the first few pages of many organic textbooks, first chapter, so talks a lot about structure and bonding. And one of the topics within structure and bonding that is quite important in organic chemistry is talking about resonance. All right, so we need to know how to draw Lewis structures and then take it one step further and understand that, as it says here, some molecules can't be adequately represented by a single Lewis structure. For example, two valid Lewis structures can be drawn for the anion that is shown here. Okay, so I'm going to make sure this is focused. Okay, so this anion, we've got this double-headed arrow here, right? That's showing the two resonance structures. Here we've got a double bond between the carbon and oxygen, and there's a negative charge on this nitrogen. Whereas this resonance structure, here we have the double bond between the carbon and the nitrogen. And we've got this single bond of the oxygen and the negative charge. It's on the oxygen. Okay. So we've got these possibilities of these two structures, right? However, neither one of those exists as they're shown there. Okay, so let's read a little bit more how the textbook explains this concept. Okay, let me get set up a little bit. I have a pillow under the book to help stabilize it. Okay. All right. Resonance structures are two Lewis structures having the same placement of atoms, but a different arrangement of electrons. Which resonance structure is an accurate representation for this anion? And the answer is neither of them. The true structure is a composite of both resonance forms. It's called a resonance hybrid. The hybrid shows characteristics of both resonance structures. Each resonance structure implies that electron pairs are localized in bonds or on atoms. In actuality, resonance allows certain electron pairs to be delocalized. This is an important concept. delocalized over two or more atoms. And this delocalization of electron density adds stability. A molecule with two or more resonance structures is said to be resonance stabilized. We'll return to the resonance hybrid in section 1.5c. Okay, so I'm going to go into resonance theory. All right. First, these general principles. These are going to help us. Okay. All right. So this introduction to resonance theory, we want to keep in mind these basic principles. Okay. Resonance structures are not real. An individual resonance structure does not accurately represent the structure of a molecule or an ion. Only the hybrid does. Resonance structures are not in equilibrium with each other. There is no movement of electrons from one form to another. Resonance structures are not isomers. Two isomers differ in the arrangement of both atoms and electrons, whereas resonance structures differ only in the arrangement of electrons. Okay, so these are all very important to be familiar with and to understand. Okay, so for example, let's look at these examples here. A and B, these ions are resonance structures because the atom position is the same in both compounds, but the location of an electron pair is different. Okay, so that's true for A and B. These are resonance structures because look at these structures. We have methyl, we have carbon, triple bond, here to oxygen, whereas here it's a double bond, right? And the positive charge is on the carbon there. So the electrons have moved, but the atoms are all in the same location. Okay. So here's our contrast example, C and D. These are isomers since the atom placement is different. See how carbon has this oxygen OH bond off of it? And D has this additional carbon hydrogen bond that's on there. Okay, so this is different. These are isomers, they're not resonance structures. Okay. All right, so for example, we could look at these and try classifying each pair, these two and these two, as isomers versus resonance structures. Okay, so if we look at this example, we have NCO, where carbon is in the center. And here we have CNO, with nitrogen in the center. So these are bonded together differently from one another. These would be isomers, right? I actually did a YouTube short on an example very similar to this, where we used formal charges to determine which structure would be more stable. Okay, let's look at this pair right here. We've got, in terms of atom placement, we have an oxygen bonded to hydrogen and both of them there. We have a carbon in the center in both of them. We have oxygen here, oxygen there, oxygen there, oxygen there. Indeed, here it looks like for both of these are anions, and the difference between them has more to do with where the electrons are. So this pair of electrons in this one up here has moved down, formed the double bond there. So these two are resonance structures. Okay, so how about some practice? Let's read about drawing resonance structures. To draw resonance structures, use the 3 rules that follow. Okay, so rule number 1. 2 resonance structures differ in the position of multiple bonds and non-bonded electrons. The placement of atoms in single bonds always stays the same. All right, so that's something we just talked about up here in these examples. Position of the atoms and single bonds always stays the same. Okay, location of hydrogen, carbon, oxygen, nitrogen, hydrogen, hydrogen, carbon, oxygen, nitrogen, hydrogen. Okay, so it's just the movement of the double bonds here and the charge. And they point that out here in these boxes. The position of a lone pair is different. The position of a double bond is different. Okay, and notice how the charge moves. That has to do with calculating formal charge. So you can determine where you would expect that negative charge to be in this case. Okay, let's move on to rule number 2. 2 resonance structures must have the same number of unpaired electrons. Okay, 2 unpaired electrons. Here, no such single one there, single one there. A and B have no unpaired electrons. Okay, if we look up here, C is not a resonance structure of A and B. Okay, so this would be considered a radical, has 1 electron rather than a pair, and same with that. Okay, so if we have pairs of electrons, we move them as pairs. Okay. All right, now let's see what rule 3 is. Okay. Rule 3. Resonance structures must be valid Lewis structures. Hydrogen must have 2 electrons, and no second row element can have more than 8 electrons. Okay, so like if we look here, this is disobeying the octet rule for carbon. In this incorrect structure, the carbon is 10. That will not fly. Okay, and then we learn a little bit here about the curved arrow notation. This is a convention that shows how electron position differs between the 2 resonance forms. And sometimes it's called arrow pushing. And this is very helpful, not just in showing resonance structures, but also with mechanisms and organic reactions. Okay, but let's look at it here. Oh, my dog is drinking out of the bowl. You might be able to hear a little bit of corgi ASMR. Okay, so let's take a look at this blue box where it's talking about curved arrow notation shows the movement of an electron pair. The tail of the arrow always begins in an electron pair, either in a bond or as a lone pair. That points to where the electron pair moves. Okay, quote unquote. All right, so here we look at move an electron pair to oxygen. Okay, so see how there's a double bond here? So this arrow is showing one of those one of those bonds that has a pair of electrons is getting moved to become a lone pair. And we can see that in the other resonance form. Here we have the nitrogen, one of the lone pairs on the nitrogen. That curved arrow is going to where there's a single bond on this side, but we see that it has created a double bond on this side, and that lone pair is no longer there because it helped create that double bond. Okay. Resonance structures A and B differ in the location of two electron pairs, so two curved arrows are needed to convert A to B. So it's going A to B. Take the lone pair of nitrogen and form a double bond between carbon and nitrogen. So that's what's happening right here. Then move an electron pair in the CO double bond to form a lone pair on oxygen. Curved arrows thus show how to reposition the electrons in converting one resonance form to another. The electrons themselves do not actually move. Sample problem 1.5 illustrates the use of curved arrows to convert one resonance structure to another. So I wanted to say a little bit more about this bolded statement. The electrons themselves do not actually move. Okay. When we're using this notation, this curved arrow notation, again, sometimes it's called arrow pushing, electron pushing. It looks like we are moving those electrons. But remember, again, what this double-headed arrow means, that the actual structure is an average between the two. It is the resonance hybrid. Okay, and we'll see more about that in a moment. Okay, let's look at sample problem 1.5. Follow the curved arrows to draw a second resonance structure for each ion. Okay, so let's look at this example A, where we have this double bond between these two carbon atoms. And this arrow is showing the double bond between these two carbons is going to get moved over and create a double bond on the other side. Okay. So the solution that goes through it shows this. Curved arrow tells us to have one electron pair. This is essentially what I just said. Then determine the formal charge on any atom whose bonding is different. Okay, this step, determining formal charge, that's going to help you determine where the charges are different. If there is a charge somewhere, like we see it right there, has it moved by virtue of moving the electron pair? So, this structure we see that there's a carbocation, positively charged carbon, okay, on this side. And once we do that, moving that electron pair, and now the double bond is on this side. If we calculate the formal charge of all of our carbons, we will see that this carbon has the positive charge now. Okay. And looky here. Positively charged carbon atoms are called carbocations. Carbocations are unstable intermediates because they contain a carbon atom that is lacking an octet of electrons. Okay, let's take a than other example. Example B, right? We've got two curved arrows tell us to move two electron pairs. The second resonance structure has a formal charge of -1 on the oxygen. Okay, so this original structure, we had a negative charge on the carbon. That turns out to be -1 formal charge because that carbon has a electron pair on it. But once we move that electron pair to create a double bond that we see over here, this electron pair moves onto the oxygen, and then the oxygen has that -1 formal charge. Okay, this resonance structure is actually quite common. We see that very often in organic chemistry. It is called an enolate anion. Okay, it's a resonance stabilized anion. Enolate. Enolates are important intermediates in many organic reactions, and because of this, all of chapters 23 and 24 in this particular textbook, these chapters are devoted to their preparation and reactions, okay, of enolates. Okay, so here's a couple example problems. We can do a little bit of practice of following the curved arrows to draw a second resonance structure for each of these. So if we look at, for example, this molecule here, we would take the electron pair from that double bond, and we would then move it onto that oxygen. Okay, creating a lone pair on that oxygen. And we see here that lone pair on the carbon, that would get moved here, creating a double bond between these two carbons here in the center. And then this electron pair from this double bond would get moved onto that carbon. Okay, so you could go through and calculate formal charges for each of these to see where there would be a negative charge by virtue of changing where those electrons are. Okay, formal charge is influenced by the number of electrons that are around each atom. So it's not surprising that the formal charge will change for a resonance structure. Okay. This problem, this is kind of fun. It gives the two resonance structures and then asks you to use the arrow pushing notation, the curved arrow notation. So here, if we recognize there's a double bond in the center of this molecule, and in this resonance structure, we see that there's a double bond here. So that tells us we would need to move the electron pair from this, between these two carbons over to these two carbons over there. So I don't have a pen or pencil with me, but I just kind of point at it. I guess I'll start here. Okay. If we look at this example, let's see, what do we got? Okay, looks like this is a carbonate anion. We've got a double bond here, and we have a double bond here. So it looks like, using the curved arrow notation, we would draw a curved arrow going whoosh, just like that, creating a double bond there. This, okay, sorry, I'm looking at this more closely. We need to create a double bond here, so we'd have one of these lone pairs that would then create a double bond here. This electron pair needs to then associate itself with the oxygen here, and that would create a negative charge. Okay, so two curved arrows, one going, the other one going like that. Okay, over here, I want to look at this again, make sure, yeah, because we have these hydrogens here, we can't move anything. These are just single bonds, those aren't going to change. So it all has to do with moving the electron pair over to this double bond. Okay, I just wanted to think through that again, make sure I didn't make a mistake that I didn't recognize at first. Okay, all is well. Two resonance structures can have exactly the same kinds of bonds as they do in the carbocation in sample problem 1.5a, or they may have different types of bonds as they do in the enolate in sample problem 1.5b. Either possibility is fine as long as the individual resonance structures are valid Lewis structures. Okay, does that sit well? Okay, we'll keep going. The ability to draw and manipulate resonance structures is an important skill that will be needed throughout your study of organic chemistry. With practice, you will begin to recognize certain common bonding patterns for which more than one Lewis structure can be drawn. For now, notice that two different resonance structures can be drawn in the following situations. Okay, so let's take a look at these more closely. Okay, this one here, let's look at this bullet point. When a lone pair is located on an atom directly bonded to a multiple bond. Okay, so here's a lone pair adjacent to this double bond. Okay, we have this lone pair there. Okay, so this lone pair can move over, create a double bond. Okay, and this carbon, of course, that can't have 10 electrons. So we have this pair of electrons from the double bond go and create a lone pair on this carbon. Okay. Then if we look at the enolate example, this lone pair adjacent to the C double bond O. Okay, that right there. That then moves, creates a double bond between the two carbons, and this lone pair moves to give this oxygen 3 lone pairs and a negative formal charge. Okay, so what's another situation? Okay, two different resonance structures can be drawn in this situation as well, when an atom bearing a positive charge is bonded either to a multiple bond or an atom with a lone pair. Okay, so here's an example, a charge adjacent to a double bond. Okay, see that charge there, adjacent to double bond. Okay, or a positive charge adjacent to an atom with a lone pair. Okay, like we see right here. There's a lone pair right next to this carbocation right there. Okay. A little bit more I want to talk about with resonance. Okay. So here's a problem it gives. It's asking you could draw second resonance structures for each species. Okay, so this is something you could practice doing with each of these. One thing I will say is with halides, halogens, they do not tend to create double bonds in organic compounds. So those, if you include those as a resonance structure, those are not going to contribute very much at all. And that is what we are about to talk about in this next section. Okay, the resonance hybrid. The resonance hybrid is the composite of all possible resonance structures. In the resonance hybrid, the electron pairs drawn in different locations in individual resonance structures are delocalized. Okay, the resonance hybrid is more stable than any resonance structures because it delocalizes electron density over a larger volume, or in other words, over more atoms. Okay. What does the hybrid look like, you might be asking? Okay. When all resonance forms are identical, as they were in the carbocation in sample problem 1.5a, each resonance form contributes equally to the hybrid. When two resonance structures are different, the hybrid looks more like the better resonance structure. Okay, notice how better is in quotes. The better resonance structure is called the major contributor to the hybrid, and all others are minor contributors. The hybrid is the weighted average of the contributing resonance structures. All right, so and then here's the key question. What makes one resonance structure better than another? Okay, let's look at this. There are many factors, but we're going to look at just the two major ones. Okay. A better resonance structure is one that has more bonds and fewer charges. Okay, so let's look at this one here, where we have this ketone. It's actually acetone here. Okay. This could be, you could use your arrow pushing notation, and you could take this double bond, take an electron pair from it, and you could associate it with the oxygen as a lone pair. Okay, but what you've done is you have reduced the number of bonds, right? You had a double bond, and you've reduced it to become a single bond. You've also created a separation of charge. Okay, so you have a positive there and a negative there. That will be less stable. What will tend to happen is that lone pair will reassociate with this single bond to create a double bond, and here we don't have a separation of charge. It is all neutral. So this structure is more stable. Okay, so let's see what the textbook says. Comparing resonance structures of X and Y. It's these two. Okay, X is the major contributor because it has more bonds and fewer charges. Thus, the hybrid looks more like X than Y. How can we draw a hybrid which has delocalized electron density? First, we must determine what is different in the resonance structures. Two differences commonly seen are the position of a multiple bond and the site of a charge. The anion HCONH, negatively charged, illustrates two conventions for drawing resonance hybrids. Okay, so one is drawing these resonance structures. that are kind of like the two extremes of what actually exists. Okay, and these are individual resonance structures. That said, the utility of drawing these two resonance structures separate from each other is that you can, in a very straightforward way, count up all the electrons as you are creating the Lewis dot structure. Okay. Whereas the resonance hybrid, this is portraying the molecule in a more accurate way. Okay, so if you look at, it's kind of hard to see. Zoom in a little bit. I'll try zooming in because I really want to show this. Okay. So what we're seeing here is essentially a bond and a half. Okay, so the bond order between carbon and nitrogen is 1.5 bonds. Bond order between carbon and oxygen, 1.5 bonds. Okay, so there are delocalized electrons creating essentially half a bond here, half a bond there. But that's difficult to add up the electrons. Like, how do you put in essentially half of a bond? It's difficult with the convention of Lewis dot. So we just draw these dashed lines to portray that. And then you can also show that there's a partial negative charge here, partial negative charge there. Okay, depending on which of the two resonance structures is the major contributor, that is going to give you some information as far as if one of these is slightly more negative than the other one. Okay. And part of that is by determining formal charges as well. Okay, and so generally, the atom that's more electronegative, in this case oxygen, that will be more stable, having more negative charge to it. So we can predict that this will be a major contributor if you base it on formal charges, and recognizing the more electronegative atom will be more likely and be more stable to have a negative charge on it. Okay, so what else do we got here? Double bond position. Structure A has a CO double bond, whereas structure B has a CN double bond. A dashed line in the hybrid indicates partial double bond character between these atoms. Okay, we just talked about that. Location of the charge. A negative charge resides on different atoms in A and B. The symbol, this is a delta, a lowercase delta in Greek with the negative sign, for a partial negative charge indicates that the charge is delocalized on the nitrogen and oxygen atoms in the hybrid. All right. So this introduction is meant to serve as, or this discussion of resonance, introduction only. Okay, and then goes on to tell you that you will see resonance again. And that is very, very true. Resonance shows up in so many places in organic chemistry. We've got it in many mechanisms, structures, many things that are relevant. So I hope that was helpful for you, relaxing for you, to read through some of these aspects of resonance and as it pertains to organic chemistry. And I want to, before I say goodbye and good night, or maybe it's morning, good morning, thank you for being here. I really appreciate all of you. If you would be so moved to like this video, leave me a comment, leave me any requests that you have. I'm always happy to take requests. And if you are enjoying this channel, do please subscribe to it. That will help more and more students get to learn in a very calm, peaceful, kind, encouraging way that I like to do. And people who learn better in that way, I'm really hoping this is helpful for you and for them. So, all right, thank you so much, and I'll see you in the next video.